I'm very pleased to start a new colloquium series, which is live here in person. Which it wasn't clear for me that will happen until very recently. And I'm very pleased that people cooperate and come here. I think the live real seminars have more advantages than disadvantages. And this colloquium may be a little sad because it's in memory of Steve Wiesner. I worked with him here about 20 years ago. And Steve Wiesner, I think, is a very important figure. He's not a standard man, but essentially the whole field of quantum information, which today is multi-billion industry, one can say started from this man. He was working with Charlie Bennett, and many of his ideas went out, not necessarily through his papers. And I had privilege to have 2 papers here when he had some part-time affiliation with Tel Aviv 20 years ago. And I choose speaker who is working on Steve Wiesner ideas. First idea of Steve Wiesner was quantum money. And this is one of the topics, if I understand, of your PhD, and no, it was later. And all Sattath has some history, I understand, connected to Tel Aviv in some way, because Julia Kempe was your part advisor, and at that time she was in Tel Aviv. Yeah. And but he finished his PhD in also with the Dorita Aronoff in Jerusalem, and had 2 postdocs, one in UC University of California, Berkeley, and
MIT.
And also MIT. Sorry, that I forgot this. And now he's assistant professor in Beersheba University, and he will talk about Steve Wiesner's idea and how they developed since then. Please.
So I'd like to thank Lev for the kind invitation. Today I'll talk about uncloneable cryptography. The question we ask is the following. So in quantum mechanics, we have the no cloning theorem. I'll explain what it is in a few slides. But it essentially says that if you have a quantum state, which you don't know what it is, you were given the quantum state, and you need to create another copy of it, well, that's impossible. Now, this statement or theorem sounds like a bad thing, right? It says that you cannot do something. But if we look at it the other way, we might find benefits in it. So that's by now the field of uncloneable cryptography, which says, okay, how can we use this property for our own good? So I'll start with the talk with explaining what are qubits and the no cloning theorem, but we'll move on quite fast to Wiesner's work, which started the field of quantum computing in some sense. And he observed that the no cloning theorem is very useful to make sure that you cannot forge money, right? This is the fact that it should be hard or impossible to copy the bills in your pocket. If this was quantum money, then maybe we could use this no cloning theorem to prove that this cannot be done, right? Rather than the way this is now, that it's simply a cat and mouse game, right? It is possible. We all know that it's possible to counterfeit money. We see it, in movies and etc. It's a multi-billion-dollar industry, actually, and we want to avoid that. So that was his idea. Then we'll see modern variants of quantum money, which extended Wiesner's idea, and then we'll move to other unclonable primitives, including tokens for digital signatures, quantum copy protection, quantum lightning, And there are many more by now. And of course, I don't expect you to understand what it means now. We'll go through, throughout the talk. Okay. So first, what are qubits? Okay, so imagine that you have a spin-half system, and we start looking at we just denote 0 as the up state and 1 as the down state. Okay, and we start thinking, okay, what if these were bits in a computer, right? What could be done in that? And actually, this was the starting point of Stephen Wiesner. He was the first to view qubits as system that, as quantum systems, as something that describes information rather than things like atoms, molecules, photons, etc. Okay. And we also define the plus state as the uniform superposition of 0 and 1, and the minus state as 0 minus 1. Right? You could think of it as the eigenstates of the X operator. And of course, if you could have a bunch of these guys, if you combine them, and that's denoted say 0 tensor plus, tensor 0, tensor minus. Right? These are more spin-half system. Okay. And now we'll start by explaining a little bit in more detail what the no cloning, or a weak variant of the no cloning theorem says. This was proved by Wouters and Zurek, and I wanted to notice the year 82. It's informally, it says the following thing. Suppose I give you an unknown state psi, and your goal is to prepare psi tensor psi. Can you do that? And the answer is no. This is a non-linear operator. All the operations in quantum mechanics are linear, and therefore you cannot do it. The proof is 2 lines, basically. If someone is interested, I'd be happy to show that at the end of the talk, but this is simply a non-linear operator. A non-linear operation, the operation that takes psi to psi tensor psi for all state psi.
What's the multiplication sign?
The tensor.
What's the operation?
So what's psi tensor psi? So this is like 2 perfect copies of psi. Okay, so this is the first system and then the other system. So imagine that you're given one system and you want to create another copy of it. That's psi tensor psi. Is that okay? Okay. Okay. So Wiesner came up with this idea of quantum money in 1969. Remember that the no cloning theorem came up only 13 years later, so it was hard to make the arguments back then. So what is quantum money? Okay. So in this setting, this is called, in modern terms, this is called private quantum money. We have a bank which generates a secret key, and it keeps the secret key to itself, right? And then there are 2 operations: mint, which creates the money. So it creates the money and gives it to the user. And then the user could come back with a quantum state. Maybe it's the real quantum money state, but maybe it's the user might attempt to perform forgery. We don't know. And there's a verification, right, which says whether to accept the user's money or not. So these are the 2 basic operations we have: mint and verify. Let's be a little bit more. Let's see how it works in detail. So the first thing we do is mint. There's a quantum algorithm. We'll see what it is in a second, that generates the quantum state. And then we want to give it to the user. Well, for that, we need a quantum communication channel. Okay, so we have a fiber that we can pass these qubits on, say, on optics, using optics. And then we send it to the user. Now the user has the money. How do we verify? The user sends the quantum state back to the bank, and the bank runs the verification algorithm and either rejects or accepts. What do we mean by counterfeiting? That's a little bit tricky.
But there's also cancellation. I mean, if you pay, then basically you need to kind of unmint or something like that.
We'll get into that in a few more minutes. Okay, exactly what does it mean, and what do we do with after money gets accepted? Okay, that's an important detail, but we'll get to that later. And I think it's related to your question, what exactly happens after verification, also partly in this slide. So what exactly do we mean by counterfeiting? So the adversary, that's why he has these, looks like a devil here, gets quantum money state. We put we take two bank branches and we do not allow them to communicate whatsoever. And now the adversary's goal is to use that quantum money state, prepare two copies, give them to the two branches and get them to accept. That's his goal. If he succeeded to make in making both of them to accept, then we say that forgery happens. And of course, what do we want? That forgery would not happen, right? That's our goal. And maybe I'll be a little bit more careful. Forgery could happen. We want that to happen with negligible probability. And there are some more technical details, and I'll try to avoid that during the talk. The talk is going to be a little bit hand wavy because I don't want to be technical.
Why do you need two banks for forgery?
Why don't I say that? So you might say, okay, maybe only one branch will. That's a good question.
I thought that the idea is that you send it back to original bank and if everything was okay, then you also send it to your own bank or whatever.
The reason is that if I don't do that, if there's a single bank, I could do it also classically. Okay, imagine how, like, you know how these coupons with these, say you go to Aroma and you buy I don't know how to say that, Cartisia in the bus. What's the name for that? Subscription. Okay, imagine that they print out random numbers. And if you come back with the same number, they give ice cream to whoever comes first with that number. Okay? Now, and then they scratch it off. So you wouldn't pass, you can show that this is unforgeable according to your definition, but it wouldn't work if you have these two separate banks that cannot communicate, right? If you have two different branches that cannot communicate, this wouldn't work. So this is a way to come around the problem that I wanted to be successful in some sense for quantum and not for classical. This is a technical way to get around this issue. I hope this answers your question. Yeah, okay, thanks. Okay, and more broadly, an adversary, he gets n dollars, should not be able to pass n+1 verifications. You could even, I think I like to think of it as some sort of a cryptographer's thermodynamics law, that the total of money in the world is non-increasing, right? That's the ultimate version of money in some sense. Okay, now let's go and discuss Wiesner's original scheme. So it uses the following states, 0, 1, plus, and minus, which I mentioned earlier. And the way that it works is that the bank picks up a random serial number, here denoted I, and a random sequence of that form, and create the associated quantum state. So, for example, the bank could uniformly at random choose something like -1, 1, plus, -0. That's your quantum money state. Of course, in practice, this should be a long string, not as that, but because we wanted to be the probability of doing it successfully to be exponentially small. So we want the number of qubits here to be large, say 100. And then the bank maintains a classical description of that state, right? So the bank keeps a classical string, -1, 1, plus, -0 in its database. This is a purely classical database, has nothing to do with quantum, right? It's just a classical string. Good. Now, how would the bank verify the money? Right? He gets some quantum state. The bank looks at the serial number, sees that the number is I in this example. And so he expects the first qubit to be minus. What will a bank do? He'll measure that qubit in the plus-minus spaces. If the outcome is plus, what would it say? Reject. He expected that qubit to be minus, right? So if he sees a plus, someone is trying to fiddle with the money. That's the wrong money, right? That's also, of course, the bank will try to stop that and reject. And so, if the outcome is minus, then he'll move on to the second qubit. He'll measure in the standard basis, the 0, 1 basis. If he'll see the outcome 0, he'll reject, right? And so on and so forth for all the qubits. That's it. That's the entire scheme. Are there questions about that?
How do you deal with errors?
Oh, that's a great question. So one of the Wiesner made the argument that it can be made noise tolerant. He didn't figure out all the details. Of course, again, I'll show you a bit later, but this was only proved in 2012, right? It took, 50 years to get right. And now we know exactly what noise level you could tolerate. It's you could tolerate 1 minus cosine squared pi over 8. It's roughly 13% of noise. 14% of noise. And the idea is that if you see that the number of errors is below 14%, you still accept, and that's still secure. Okay, great. Thanks for the question. Yeah.
Why do we need both P bases and X bases to one of them?
Great question. Can someone give an attack? Suppose we only use the standard basis. What could you do then? So remember the definition of forgery. Oh, I'm going the wrong way. Sorry. So basically, you need to pass 2 verifications, right? That's your goal. So you're handed out 1 copy, and now you want to pass verification twice. So what would you do? So suppose the state is 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, and you know that it's in the standard basis. What will you do? I think the answer was given by someone at least. You measure in the standard basis, realize the state of all the qubits, and prepare another copy. Right? That's too easy. Okay.
I wanted to kind of ask the opposite question of what he asked. So why just 2 bases? Because in principle, you can choose a different basis randomly for each qubit.
You could do that, but that's a more complicated scheme. You could do that, definitely.
I mean, is it giving you any more benefit, or is there some way to see that?
Let's do it offline. I can explain. There's only a very, very non-important benefit. Let's put it this way. You get slightly better parameters for unforgeability. Of course, at the cost of added complexity to your scheme. Okay, so the intuition for the proof is that the adversary doesn't know in which basis each qubit is, and there's disturbance information trade-off. If you're trying to learn about the state, you necessarily disturb it, and therefore, kind of intuitively at least, it should be hard to do. And indeed, in 2012, there were 2 different proofs, never mind the details, that show that the scheme is secure, even when you the noise tolerant version. Now we could ask, and I think, what was your name? Sorry, what's your name? Danny. I think this is related to your question. What exactly do we do with the money? So is it like cash? If you go to someone and give them the money, they might return it back to you, right? You don't throw away the money, right? And it turns out that if you use quantum money, you need to do that. You could never reuse the money. That's the only way that security is proven. Notice that it says it is secure if valid money is replaced after successful verification, right? So you cannot reuse your bills in some sense. And now there are pretty simple attacks. There's actually 2 attacks if you do not do that. So suppose you you could go to the bank, give them a quantum state, and they give it back to you and tell you whether it was accepted or rejected. Then in that case, there's a pretty simple attack. I encourage you to try. I'll be happy to explain it in detail after the talk. It's a really nice, this is a nice question, I think. And it turns out that even in a more restricted model, when money is returned only after a successful verification, so you don't get back the money which is invalid, you only get it if it's valid. Then there's also an attack. And I will explain that in next. And interestingly, the idea here is, okay, wait. So first, let me explain again in more detail the setting. So you could go to the bank, give the bank the money, and the bank will run the verification. If verification fails, you're sent to jail. That's it, game over. Okay. If it succeeds, then you get back your money. And it tells you, yeah, it passed. Otherwise, it would have been in jail, right? So you probably know that. And the question is, can the adversary pass through verification? Now, intuitively, this might seem hard because if you try to fiddle with the money, you might change it and then end up in jail. And if you don't do anything with it, then you haven't learned anything, right? You sent it to verification and it came back. But this intuition is wrong, right? And interestingly, the attack is based on the Elitsur-Vaidman bomb test. And there's a variant which I will not describe. Again, I'll be able to do that after the talk, that is based on protective measurements, which is that even works in a slightly more general setting, but again, I won't get into the details. So I want to explain for those, maybe all of you know, but perhaps not, the Elitsur-Vaidman bomb tester. So I'll give you my interpretation. I'm pretty sure that Lev would present it very differently than the way I'm going to do that. So it's perhaps a slightly different perspective on it. So what's the setting? So you will eventually be given either a bomb or a dud. And the important thing is, how exactly do I model what a bomb is and what and what a dud is, nifl in Hebrew. So first, what is a bomb? So we have, you see here that we have an input wire. You should think of it as that's what's going out of this bomb. And this is the inside of the bomb. Like, oh, it's going too slowly here. I don't know why something here isn't working as fast as it should. Okay, so this is the inside of the bomb. There's like a wire going out of it, okay? And now, in the inside of the bomb, there is a qubit initialized to 0. Okay. Now, let's see what happens. This is a controlled X operation. This means that if the first qubit is 1, the second qubit is flipped. If the first qubit is 0, nothing happened to the second qubit. That's why you call it a controlled knot, a controlled X. Right? We flip the second qubit only if the first is 1. So let's see. What happens if we input the wire 0? So 0, nothing happened here. The control X doesn't do anything because that's what we said, right? If it's the first wire is 0, we don't do anything to the second wire. And it started in the 0 state. Now we measure the second qubit. If the outcome is nothing, it is 0, we do nothing. Oh, it's slightly hiding the, give me a second. I don't know if this is my screen. There. Can we move the, should I don't know. Yeah, that's better. Right, so if the outcome is 0, which is what happened now, oops. Right, we measured the bottom qubit, the outcome was 0, so nothing happens. Let's see what happens if the input is 1. So again, if the first wire or the top wire is 1, we flip or apply a knot to the bottom qubit. So it was 0, we apply a knot to it, changes to 1, we measure. What happens? Boom. That's the mechanic of, that's how a bomb works. If it's 0, nothing happens. If the input is 0, nothing happens. If the input is 1, it explodes. Pretty much, I would say this is the bomb, right? Does that make sense so far? Okay. How do we model a dud? So again, we have the same kind of structure, except this part doesn't work. It should have been control X, but actually it's control identity, meaning it doesn't do anything. Control identity doesn't do anything. So you could just ignore this, this part. So some part of the bomb isn't working, therefore it's a dud, right? Does that make sense? Hopefully it does. So let's see what happens in a dud. Well, if the input is 0, nothing happens, right? The 0, it remains 0, we measure it, the outcome is 0, and therefore it would not explode. But also if the wire is 1, right? It doesn't, the information is not passed to the second qubit, and therefore it's also like, it won't explode. And I hope you will all agree that this is how a dud functions, right? No matter what you put as an input, it never explodes. This seems like a dud, right? Good. Now, your goal is you're given either a bomb or a dud, And your goal is to distinguish between two cases. Now, of course, the easy solution is to press the button, right? That's the easy solution. What's the problem with that? As I'm sure you all know, some of you know. So maybe there are two problems. One, you might get hurt. Second problem, well, maybe you want to keep these bombs for use. You want to use them. So in both aspects, it's pretty bad. So you want to check whether it's a bomb or not without it exploding. Good. Can we do that? So Kviat et al. Gave the protocol which works with probability of exploding the bomb that goes to 0. And now I'll describe how their algorithm works. So here you see this is right. This is a DAD. This is the bomb case, right? And the algorithm says the following thing: start like with an input which is 0, right? Rotate it by a small angle delta, which is pi over 2n. It's like a small angle. And then just check what happens, right? Apply the bomb. See whether it explodes or not. And of course, if it's a dud, nothing would happen. And repeat that many times, right? So you see that the algorithm, the outside of the algorithm is the same, right? The only thing which changes is whether it's a bomb or a dud. And let's see what happens in both cases. So if it's a dud, we apply the small rotation delta. This part doesn't do anything, right? This is the identity. So nothing happens to these qubits. And of course, the bomb would not explode because it's a dud. And then we repeat it n times. And remember, the angle is pi over 2n, and we repeat it n times. So we apply a small rotation and repeat it many times. Right? Overall, what will we get after n repetitions? Right? An angle of pi over 2, right? 90 degrees. So 0 would go to the 1 state. Okay? And now we measure that qubit. What will be the outcome? 1. It started with 0. Every time it rotates by a small angle delta. We measure, the outcome will be 1. And in this case, we'll say it's a dud. Now let's see what happens in the more interesting case where it's a bomb. If it's a bomb, here we start with 0. We rotate it by a small angle delta, and we apply a control x. Now, the thing is that we'll have like the state will, after this application, right? After applying this step, right? At this point, before the measurement, the state would be cosine delta, sinus delta, cosine delta 0, 0, plus sinus delta 1, 1. And now we measure right? There's a measurement happening here, right? So what would happen? With high probability, it would not explode and collapse. The state would collapse back to 0, 0, exactly where we started with, right? So it will not explode. And you could do the calculation. It's pretty easy that actually it will, with high probability, it will not explode in all the rounds, right? So basically what happens is, you start with a 0, you change the state to a small angle delta, but the measurement causes it to collapse, and you do it all over and over again, right? So even after the last repetition, it would be in the 0 state. And then when you measure what it is, the outcome will be 0. And then you'll say that it's a bomb. So these are the two cases. Remember, before the state would go from 0 to 1, here it would just almost stay at 0 all the time. And that's the way that you distinguish between the two cases. And you could do the math and see that the probability of it exploding goes to 0 as delta goes to 0. That's it. Okay. So how can we use that for the attack on Wiesner scheme? So it's the same idea as the bomb tester. Here we suppose, let's see what happens in two cases. Suppose alpha is the plus state. The interesting aspect is that applying an x to the plus state doesn't do anything to it. It's an eigenstate of it with the eigenvalue 1. So flipping, if you have 0 plus 1, when you flip it, of course, nothing happens to the state. So this is exactly like the DUD case, right? Control X doesn't do anything to that. So it would go on and on. And it turns out that in the 3 other cases, it's exactly like the bomb case. So you can identify whether the state is plus or the 3 other possibilities with the probability of it exploding or you going to jail going to 0. Okay, that's the idea. Of course, you could repeat this attack to identify whether it's -0 or 1, and never repeat that for all the qubits without going to jail. That's the idea of the attack. Of course, I won't get into the details, but I hope the idea at least is clear. Somehow there's a correspondence between the attack and Elitzur Vaidman's bomb. Okay. Now I want to move on to more modern topics. Again, this will be only a bird's eye view of these things. So one interesting aspect is quantum coins. We have quantum bills and quantum coins. These are 2 different things. Any ideas what's the difference? What's the fundamental difference between a bill and the coin? Again, fundamental difference between coins and bills. Sorry? Yeah, that's the fundamental difference. Why is it important? So again, coins are indistinguishable from one another, and the bills are distinguishable. And why is that important? Especially from a privacy perspective, right? If there are serial numbers, you can be tracked, basically. And I would say quantum coins are also interesting from a more fundamental perspective, because to kind of create a quantum money scheme where each money is different, you need basically the no cloning theorem. For quantum coins, you need some sort of a no cloning on steroids, in the sense that you need that even if you're given n copies of the state, you cannot create another copy. Right? The original one said if I hand you out a single copy, you cannot create 2 copies. Now I need a stronger variant that it holds even for lots and lots of copies. So you cannot do things like tomography and stuff like that. Okay. There are another variant is classical minting. Here, right in the beginning, we said that the bank creates the money and sends it to the user. In classical minting, it's an interactive protocol between the user and the bank that uses only classical communication. So in some sense, the user prints its own money, which could sound something like fishy, right? Why couldn't it repeat the process and create 2 copies of it? I won't answer this question at this time, unfortunately. And another variant is classical verification. So it's the same thing, but for verification. The bank asks the user some question. If the user answers correctly, it accepts. Okay. So again, we don't use any quantum communication channel. I just hint towards the idea. The idea is that in order to answer correctly, you have to measure your state and therefore destroy it. So again, I hope this kind of answers your question of how. So and in particular, you cannot reuse it. So now the verification itself kind of destroys the state. Okay. And recently we defined a notion of semi-quantum money, in which we have classical verification and classical minting, and we call that semi-quantum money. Notice that in this setting, the bank is entirely classical, right? So the bank is classical. He's telling the user to what to do, but he doesn't need any quantum infrastructure whatsoever. And this uses an interesting technique, very important technique called Clough trapdoor function, which was introduced recently, but I won't explain that. Another variant is public quantum money. right? So far, we said like the verification is done by the bank, which is kind of similar to what happens in a credit card. You know that you need the bank to answer whether a transaction is valid or not. In a public quantum money, the bank issues a secret key and a public key. All the users have the public key. And now, of course, the bank would mint the money, give it to the users, but the users could verify the money themselves using the bank's public key. So even though they know or they could tell whether a banknote is valid or not, they couldn't forge it. This is somewhat harder to do.
But you still need to destroy it.
No, it's not destroyed. No, this way it's not destroyed actually. It's a quantum verification algorithm and it does not destroy the state. Okay, and I guess I want to say that we still don't have any constructions for this based on standard hardness assumptions. For those that know what that means, it means basically this problem is still unresolved. Right? I'm not claiming that we know how to do it properly. We have candidate construction, but it's not so not in a very good shape.
You are telling me to us we are not supposed to understand the why. So
why?
I know what you just
why is it?
Yeah.
Okay, I'll try to give a few more details.
No, I just said I didn't miss something.
No. This is
You just told us some statement.
Yeah, this is intended for people either that comes from cryptography or computational complexity. They, I'm pretty sure, would know what that means.
Okay.
For the others, I prefer not to get into that. Good. Okay. Okay. Another variant combines the two things I mentioned before. We had quantum coins. We had public quantum money. So far, we didn't have any constructions of a public quantum money scheme. So recently, we did that. We almost did that, I guess. We showed a way to lift private quantum, any private quantum coin scheme to a public quantum coin scheme. This is based on a work by Henri Shmueli. He isn't here, right? He's from Tel Aviv University. He's a PhD student at Tel Aviv University. So he came up with a private coin scheme, and we use his scheme to construct a public coin scheme. And what's the idea there? It is pretty simple, actually. So suppose you go to China and someone gives you, or I don't know, Taiwan, you've never been there. Someone comes up with 100 Taiwanese dollar, I don't know. How would you verify it? So the idea is, probably you went to the bank or to the ATM and already took, a few $100 from the ATM that you trust. And now someone comes up and brings you another dollar. What would you do? Compare. So we call that comparison-based verification. So that's basically what we do. How can you compare quantum states? That sounds a little bit trickier. How do you know if this one is like the other? So this is pretty not well-defined question, but it turns out there's something called the symmetric subspace. You could check that if you have a bunch of registers, that they're symmetric with respect to permutation. So that's basically what you do. That's it. So why do we call it almost public quantum money? For two reasons. First, you have to already own money in order to verify. It's a bit strange, but okay, that's what we have. Another thing is that it's only rationally unforgeable, meaning there is actually a high probability that you will be able to forge, but on expectation, you're going to lose. Kind of weird. Okay, so that's why it's not, I wouldn't say this fully resolved the problem, but still something interesting is happening. Okay. And now I have 10 more minutes to tell you about more, more abstract notions. So you should think of quantum money as the first thing, or you want to have just a state which is uncloneable. Recently, there are several ideas of how to add functionality. So the first thing you want is that you have quantum states that cannot be copied, but you want some added functionality from that. And we'll see a few examples of what such functionalities could be. Okay. So the first one is called quantum tokenized signature. schemes. And I'll tell you a story for that to explain the idea behind. The fisherman caught a quantum fish. Fisherman, please let me go, begged the fish, and I will grant you 3 wishes. The fisherman agreed. The fish gave the fisherman a quantum computer. That's the thing you see here, right? That's the or here. And 3 quantum signing tokens. These are the quantum kets over here. These represent the rubber stamp. The fish explained, to sign your 3 wishes, use the tokenized signature scheme on this quantum computer, then show your valid signature to the king who owes me a favor. The fisherman used one of the signing tokens to sign the document, give me a castle. So you see here, this is, of course, the quantum computer. I hope you see the rubber stamp here. And before, you see that there's no signature. Importantly, and after, you see a classical signature added to the document. And you see that the state itself is consumed during this process. So there's a measurement happening behind the scenes, which destroys the state, right? That's why you cannot use it. And rush to the house. The king executed the classical verification algorithm using the fish's public key. Okay, so again, behind the scenes, the fish has a secret key and the public key. The king, who knows the public key, could verify the signature using a classical computer. That's a completely classical part. Yeah, that's it. And since the signature was valid, the king complied. The fisherman's wife wanted to sign 10 wishes using their 2 remaining signing tokens. The fisherman did not want to cheat and secretly sailed to meet the fish. Fish, my wife wants to sign 10 more wishes. But the fish wasn't worried. I have learned quantum cryptography following the previous story, The Fisherman and His Wife by the Brothers Grimm. The quantum tokens are consumed during the signing. Your polynomial wife cannot even sign 4 wishes using the 3 signing tokens I gave you. Yeah, so that's it. That's the end of the story. I'll try to explain again what's the challenge here and what are we doing here. So the fisherman should be able to sign at most 3 wishes. Now, if we use a digital signature scheme, we could achieve something similar. The fish could have a secret key and a public key, and just hand over the secret key to the fish, to the fisherman. But what's the problem here? If the fish just gives his secret key to the fisherman, what would be the problem? Sorry? How many wishes could he sign? Infinitely many, right? There's no bound on the number of valid signatures that he could produce. So the idea is that if you give these quantum states, right, each time you want to create a signature, you have to measure them and therefore consume them, and that's the idea behind this story. Okay, and of course it cannot be achieved classically. Sorry, again? Good. Good. The idea here is that he couldn't produce any valid signatures to everyone, right? So maybe you're saying, oh, but then he could go to someone else, maybe the prince, and show him another signature, right? So, think of the people that you're trying to convince that you have signed messages, that they are different. So you cannot say, oh, just don't accept the 4th message, whatever it is, because maybe he asked the prince for a castle, the king for diamond, and the queen for whatever. There might be many parties involved. I hope this answers your question. But you're right that the story doesn't give this answer. Okay, thanks. Okay, so very recently we had a construction for private tokenized signature scheme. So here it's the same story, but now the king needs the fish's secret key in order to verify. And interestingly, this construction is based on Wiesner scheme, and it's so simple that I could easily explain it. The tokens are simply the states we mentioned before, zero, like random string, like random qubits in random basis. And to measure, so now the goal is simply to measure 0 and 1. That if you can try to come up with something which can be used to sign bits, there are standard techniques to make it so you sign arbitrary documents, which I won't explain. So the goal is only to sign a single bit. And how would you sign 0? Measure all your qubits in the standard basis. If you want to sign 1, measure all your qubits in the plus minus basis. That's pretty much the entire scheme. And we can show that this construction is noise tolerant and practical. And in fact, there's an experiment happening these days with Alina Karabachevsky actually demonstrating this construction. Okay, I have a few more minutes. I think okay. I'll move on to. Okay, I'll try to present both. What is quantum copy protection? This is very interesting. I think this is a compiler which takes a program, right, a classical program or a classical circuit, and produces a quantum state. The quantum state can be used to evaluate the circuit, but you cannot share it with others. Right? You could maybe lend it to your friend, but then it's not yours. You can do, so if you're given one copy, you cannot create two copies, which would both evaluate the function at, say, some random points. That's the idea of quantum copy protection. This is only a partial list. This is heavily studied these days. We have some partial results. And again, of course, could be generalized to like n copies. So if you create n copies of the program, n plus 1 parties should not be able to compute the function at random points. And the last thing I think is actually the most interesting. This is called quantum lightning. And the motivation is this famous Gilbert cartoon, where you come up to an office and someone is claiming that there's this guy is their random number generator, which outputs 9999999. And of course, how could you tell whether it's a true random number generator or not? And there is a recent construction by Mark Zandri, and actually Farhi et al. Also gave this construction, although they didn't present it this way, which is relevant for this problem. So here you get a quantum lightning is a pair, a string R, which represents something which is supposed to be random, and a quantum state. The quantum state is a proof that the process that generated this random string has high mean entropy, or just has high entropy. I hope this is this might sound too good to be true in some sense, but that is what it is. There's an algorithm which takes this pair, the randomness and the quantum state, and if it gets accepted, it means that the process that generated this pair, and if you look at the random, like the R there, that thing, if you look at the probability distribution that this process creates, must have high mean entropy. Okay. I can explain again, maybe offline, how does it could work.
The dollar is the lightning.
Yeah, the symbol there is the lightning. Yeah, it might look. Oh, sorry. Yeah, it should have been a lightning. Sorry, my bad. That's a typo. That's it. Thank you for your attention. Thank you.
These things will turn out to give us the capability.
Yes, but all the private money does not. But public quantum money, I would say yes, because it gives privacy. And it works also offline, right? So the fact that it works offline is a nice addition, but it's also beneficial from a privacy perspective. More questions?
I understand that it all depends on being able to produce a quantum state
Sure.
to begin with. What if you cannot produce a true quantum state?
My starting point, I guess I should have said that I have several starting points. First, is that I assume that my adversaries are computationally bounded. Honest parties could use polynomial time quantum computation. And I don't care about events that happen with negligible probabilities. These are the three caveats that kind of I have to assume, which is pretty standard in quantum cryptography, but you could, of course, tackle these things. I don't want to get into battles regarding these questions. Actually, I'd be happy to talk about it. I have some comments about it, but again, this is kind of orthogonal to the topic that we described here. Yeah.
So in your last slide with the lightning,
Yeah.
and the entropy.
Yeah.
So supposedly that to determine that you have to look at your generator and look at a whole sample.
No, that's the nice thing.
How can you know the entropy just from one sample?
I don't know, but it's not even defined,
one
right?
random number.
Well, there isn't an entropy for that number, right? That's, I guess, your. So the claim is very tricky to understand. The claim is that if this algorithm, if this verification passes, says that procedure or the process that generated that number, if you could have repeated it many times, right? So imagine a program that looks like print 17756. This we all agree that has no entropy. The process we generate, the argument is not about the random number itself. It's about the process we generated it. That process must have Vaidman entropy. You're saying, how on earth could you say that the process we generated something? So the idea here is kind of related to quantum money, but flip the roles around. If there was another way to verify suppose this this procedure didn't have Vaidman entropy, then it essentially says that you could have repeated it twice and then create two of these lightning states. And this is forgery. So in some sense, you could think of quantum lightning as a variant of quantum money, but the roles are flipped. Before, we thought of R as something that helps you to verify the money. Here, the roles are flipped. You should think about the money as something that helps testifies that the procedure regenerated R has Vaidman entropy. But actually, I think it's extremely hard to understand. I think this should be done offline.
Maybe just one. I think we can prepare a quantum state, but your procedure requires more hardware. One is quantum storage, clear. But question: do you need really full-fledged quantum computer for most of your results, or the only thing which needed for all this money is just quantum storage?
Okay, so definitely for everything that I talked about, if you think about it as money, so money has a function as a store of value. You need to store it for long periods of time. That's out of the table. For the only thing which I think is practical is the the private tokens for digital signatures. That does not necessarily require long-term quantum memories. It is noise tolerant. It could be done with current technologies. It's just a question of how interesting this notion is. That's debatable, but it is practical. All the others are, and especially the quantum lightning here, these are completely, these require like serious quantum computers. Even like probably a million qubits wouldn't suffice. So this is like a long-term goal.
Okay, let's hope we will live till then. Thank you.